Hi Year 11s, this is Mr. Lim here again, and this is our 9th video in the hydrocarbon series about the physical properties of hydrocarbons. Alright, so let's get started. The physical properties of hydrocarbons. Okay, we're only going to deal with melting and boiling points in terms of trying to explain stuff, and also the insolubility. And we're really not going to explain stuff yet because we're going to deal with that in another topic later on. Just going to kind of list out what's the properties. Okay, so let's have a look. Hydrocarbons are covalent molecular substances, which means they follow the general rules for chemical bonding in regards to electrical conductivity and malleability. So effectively, the hydrocarbons, they're not going to conduct electricity because they're all made up of neutral molecules, which are unable to act as mobile charged particles and therefore cannot conduct electricity in any state. All right, and then in terms of malleability, they are malleable because they have non-directional bonding, because they have and so therefore the bonds can be the bonds still exist when the molecules are moved around each other, and so therefore they can be changed in their shape without the bonds being broken. All right, however, let's go to their melting and boiling points. Their melting and boiling points can vary greatly due to their size. Okay, the larger the hydrocarbon, the higher its melting and boiling point will be. So effectively, decane compared to methane will have a much higher boiling point, and that's the general relationship that you need to know, right? As it gets longer, is a higher melting and boiling point, right? Why? This is due to the weak intermolecular forces holding them together, which are the van der Waals forces. They increase in strength when the molecules are larger. And the reason for that will be explored in another topic, intermolecular forces, right? But you just have to know that the force that holds them together gets stronger when when the chain is longer, right? Another thing to note is that long and skinny things have a much higher melting boiling point than kind of short round things. All right, so here we have both C5H12. All right, they're the same size, but this one here will have a much higher melting boiling point because it's a long straight chain compared to a short round thing. Okay, but that's not really going to come up until we get to intermolecular forces as well. All right, but that's the idea. Bigger, higher intermolecular force. All right. Hydrocarbons are also insoluble in water. Okay, so this is why oil and water don't mix, right? So that means that if you mix an aqueous solution of something like salt water with a liquid hydrocarbon, you'll get two distinct layers or phases forming. So phases is the word that we use for layers, right? So just like if you've ever seen oil floating on top of water, the same thing will happen when you have a liquid hydrocarbon and water or a solution of something, right? And again, we're going to explore this more in aqueous solutions. Okay, so hydrocarbons are generally less dense, actually always less dense than water, and so they will float on water, so they will be the upper phase. All right, so anytime you add a liquid hydrocarbon to water, it's going to be less dense and it's going to float on that water, and so therefore it's going to be the layer on top. And so when you're talking about and describing the layers, the layer on top is going to be the hydrocarbon, and the layer on the bottom is going to be the aqueous solution or the water. All right, and that's it. Well, let's get on to the next one. Adios.